My name is Pedro Rodrigues, and today I will show you the electronics project we developed. In the requirement stage, we chose to build a modular, versatile, and low-cost project. In this way, we create our multi-mission platform, a set of interchangeable modules capable of providing all the necessary resources to support the operation of different payloads in their different missions. This platform was developed based on PC-104 standard, widely used in the aerospace industry and the other branches of the industry, making it capable of supporting and interacting with the most different COTS modules on the market. It was organized as follows: OBC, TTNC, EPS, THM, and ADCS. These subsystems make up our PMM, but we also have other electronic subsystems working together with PMM, but as part of the mission's payload, which in this mission will be our biological microfluidic experiment.
Hello, I'm Marcelo Moura and I'm Minerva UFRJ's mechanics researcher. Well, our project is based on a practical and modern CubeSat, where we use the stack configuration. In this one, you can analyze electrical and experimental components one by one without many problems with assemble and disassemble of the satellite. With just some pressure from above and below the CubeSat unit, you can keep all the components steady and put it inside the major structure. We developed an original structure for our team, which is shown here in figure 2. It is light and resistant to high accelerations. Our main objective is to project and fabricate a functional structure suitable for shipment into space, and in order to do so, as I said, we want a more modular feature. We need to idealize a module to carry the biological experiment under its dimensions and specifications. Not less important, our structure should also be resistant to space environmental factors, such as microgravity and solar radiation. Here in figures 3 and 4, you can see the connector and lead parts, basic parts of our main structure.
My name is Brenda Ferrari, and I am a chemistry PhD student and Minerva UFRJ payload manager. To study life in space, first we need to understand how life behaves in such extreme environments. The use of microchips make easy to send cell culture in CubeSats to space, which has already been explored in PharmaSat and BioSentinel missions. Thinking in a way to explore the subject in a general way, our team has the objective to elaborate a microfluidic platform for different biological experiments submitted to hypergravity or microgravity. So we need to fabricate the platform to validate it with experiments on cyanobacterial growth and with electronics and structures teams to develop a platform that will serve as support for coupling to a CubeSat aerospace approved. The list of requirements of the microbiosat mission starts at the fabrication with the project and two-dimensional characterization of the microchip. The validation includes the microchip integrity tests, sensors calibration, cyanobacterial growth curve, and all conditions explored until ready to integration.
Hello, I'm Caio Siqueira, project manager of the mBioSat. I'm going to rapidly introduce its main aspects in terms of systems engineering. Here you can see some examples of the three subsystems' functional requirements. The electronics team has to ensure that the CubeSat acquires and transmits its sensor data. Additionally, the structures team needs to build a 775 T6 lightweight structure, less than 500 grams. And last but not least, the payload team needs to build PDMS translucent micro device for optical analysis of a cyanobacteria. The electronic subsystem was divided into 5 subgroups, which are responsible for acquisition, processing, and transmitting data. Also thermal control, power supply, and an attitude determination control. We use a SP32 for microcontroller, a LoRa module for telemetry, 1865 lithium batteries, MLI, an active thermal control, and 3-axis reaction wheel. The STR team developed a 2U CubeSat form factor structure using 775 alloy. The structure weighs 362 grams and withstands 14J RMS accelerations with a security factor of 2. The PLD team designed a translucent micro device with 8 wells, capable of measuring the growth of a cyanobacteria. This growth will be estimated by emitting light with a LED over the cell and measuring with a phototransistor how much of it passed through the cyanobacterial culture. To validate and certify our CubeSat, the microbiosat will undergo a series of tests, inspections, and analysis, such as vibration tests, software benchmark tests, thermal vacuum cycling tests, cell growth, and much more. This will ensure a high technological readiness level. The microbiosat is under design and development since early 2020. We finished Phase A, concept and feasibility studies, and Phase B, preliminary design and technology completion. During 2021, Phase C, final design and manufacture will be completed. Phase D, system assembly integration, validation and verification will be executed through 2022. Lastly, Phase E, operation and sustainment during 2023. The project budget is shown in the chart below. The main costs are due to the electronics components followed by the aluminum and microfluidics material. The total amount is $20,550. It is possible to build up to 4 microbiosats. Thank you very much for the opportunity.